Our project aims to answer the question of what if sand was your only input method to a game. Throughout, we have contended with what such a game would look like and how to best utilize the technology we created, whilst also building an intuitive experience that appeals to all skill levels. With that, we present to you what is most likely the first sandbox controlled game in the world, created in only 12 weeks. At its core, the game revolves around the Kinect V3's capabilities. It provides both depth and RGB cameras that we use to accurately map the topology of the sand, ready for 3D reconstruction. Using this depth image, we can extract the height data, which forms the basis of our terrain generation. However, in order to reduce spatial and temporal noise, as well as mask out the player's hands, we apply several computer vision and image processing techniques, as well as hand tracking. One issue we found was a flickering effect due to random noise in the depth readings from the Kinect. We tested out many image processing techniques for this, eventually deciding on low pass filtering and the exponential moving average, or EMA. EMA is known to create a lagging effect, so to maintain good responsiveness, we attenuate its effect for regions where there is lots of activity. We called this technique EMA attenuation. Another key challenge was masking the user's hands, arms, and head from the topology of the in-game sand. To identify the user's arms and head, we threshold the depth image and then dilate it to avoid artifacts at the edges. We use Google's Media Pipe library to find the bounding box of the user's hands, and we estimate the location of their wrist with vector arithmetic. Finally, when we update the mesh, these masked regions are left the same instead of updated to the new height. We also use Google's Media Pipe to find the position of 21 key points, referred to as hand landmarks, on each of the user's hands. Media Pipe's output has several glitches, which we correct with heuristics and clamping. We use vector arithmetic to calculate the correct rotation vectors to animate each joint individually in-game. MediaPipe's hand landmarking solution is not available for C#, so we use interprocess communication to share data between a Python script and .NET. The RGB video stream and the hand landmark coordinates are transferred using shared memory. For communication and synchronization, we use the Win32 API if running on Windows, or POSIX IPC if on Linux. For Linux, this meant using external C functions in Unity via libc to access POSIX IPC. We favoured Linux as it allowed us to run the MediaPipe model on the GPU, achieving more than twice the performance compared to CPU inference. By doing all of the aforementioned techniques, we get highly efficient data exchange between the two processes that results in minimal latency and real-time responsiveness that all comes together to create a smooth and immersive experience in-game. In order to facilitate testing on devices not plugged into the Kinect, we created a noise generator that updates a height map in the same way as the Kinect, but samples from a Perlin noise function instead. Our map is split into a customizable number of chunks with a specified size and resolution. When the game starts, each chunk generates its own Unity mesh from a list of vertices and triangle indices. Chunks have Unity colliders attached to them so that our physics-based enemies are able to interact with the terrain. Each time the Kinect or noise generator updates the height map, the chunks update the height of the vertices in their mesh to match. For Unity to efficiently perform physics calculations in real time, the collider mesh needs baking. Our pathfinding system uses a producer-consumer model to process and distribute paths to enemies. When idle, enemies request a path from their position to the objective. The enemy manager works through these requests and returns a path found by an A-star algorithm, weighted by a different heuristic depending on the enemy type. Generally, these heuristics discourage walking up steep slopes or flying into terrain using the height data from the Kinect. To improve the look and feel of our game, we created our own version of a toon shader and the corresponding materials. We then color-coded enemy units based on their function and speciality. We also used Unity's visual effects and shader graphs to create custom effects using only the default particle asset for a more toony look and feel, whilst having full control to customize assets to match our game more closely.